So we're going to expand on now in some of the switches and things we turn on with the muon detection, but at the moment we still have the pulse generator on, and this wire here is still connected to the LED, which is adjacent to the scintillation plastic in the detector. So the LED is still sending the sort of simulated nuclear events down the throughput of the data acquisition system. And let me tell you now what we can do to further take ourselves closer to detecting muons. But before I do that, let me just make sure you can see on the oscilloscope that nothing has changed with the last video. The LED is still pulsing, and this is one of the timing pulses coming in from the preamplifier. So we're still operational. Okay. So if I go back now to this instrument here in the center, the pulse generator, you notice something kind of interesting, that this knob right here says single and double on it, single and double. So in other words, what's nice about this pulse generator, it can certainly generate a single pulse, which it's doing now, but if I push this switch down, it'll start generating double pulses. In other words, 2 pulses at a time will get sent to the LED, and of course I can control, the top knob is the frequency. It doesn't matter if I'm single or double pulse. I have it at 1 kilohertz, so 1,000 pulses per second. But the knob right below that one, this one right here, is the delay. So I can set the delay I want between the 2 pulses if I have it in double pulse mode. So let me just go ahead and do that then. I'm going to push this thing down to double pulse. And when I do that, let's go up and look at the oscilloscope. So there's the oscilloscope. Let me turn off channel 2 just for a moment. There we go. So if we look at the oscilloscope then, you can see that indeed we're getting 2 pulses out of the system now. So I'm going to put my hand back on the single double pulse switch, that is. So I'm going to switch it back up to single. See, we only get 1 pulse. Now I'm switching it back down to double. See, there's 2 pulses. Okay. And the other knob that's kind of interesting with this is this delay knob right here. So this delay knob allows me to set the delay between the double pulses, which is the mode I'm in right now. So I'm going to go back to the oscilloscope display right here, and I'm going to start swinging that, turning double pulse knob. So if I turn it like this, you see I have a very small delay between the 2 pulses. If I turn it all the way over to here, I have a very large delay between the pulses. And you can read on the oscilloscope, given the times for division, what timing we're talking about here, but it's kind of fun to play around with. So I can just vary the delay between the double pulses. And when you go back down to this setting here, the black knob, you can see several settings on here. 1 microsecond, or excuse me, 0.1 microseconds, 1 microsecond, 10 microseconds, 100 microseconds. That's sort of the maximum for the range. Then you can use this red knob here to dial in some fraction of that. So we're going to always keep this at 10 microseconds, and the reason we're going to do that is because the muon decay lifetime is about 2.2, 2.6 microseconds, something like that. So we don't really expect to be bothered too much by any events that are greater than 10 microseconds, so we'll sort of use this scale. Okay, so once again, if I go back to the oscilloscope screen, you can see that I can just totally vary the delay between the pulses. Now, why am I doing this? Well, the reason why I'm doing this is because in the muon detection, the core logic is that we're looking for pulse pairs like this to come from the scintillation plastic. The first pulse would be when a muon hits the plastic in the first place. It'll make a little scintillation spark which will get detected. And then if it is a muon, when the muon decays, that'll make another scintillation event. So again, the first scintillation event we'll expect is the muon just stopping in the scintillation plastic, and the second event we get is when the muon decays. So that's the core logic of detecting muons, is you need somehow to be able to process these pulse pairs that come in, and only if you get a pulse pair is it sort of probable that it was caused by a muon stopping and then decaying in a scintillator. Anything else would just make, say, 1 pulse. Some stray cosmic particle, maybe some excess charge, a gamma ray, whatever might stop in the scintillation plastic would likely only produce 1 pulse, but it's the muon doing the stop and the decay that would likely cause 2 pulses. So in the next video, I'm going to show you how we work with these pulse pairs to see, hey, is it really a muon?